All right, good morning. So we're going to be going over the second lesson to do with energy. Our first was work and power. And if we recall what work is just force times some distance that you go. So it's a force that you work against over a certain amount of distance. Okay, and this unit was called a joule, and it was also synonymous with the word energy. Okay, so work and energy kind of mean the same thing. Work is the capacity to, or energy is the capacity to do work. Okay, it's the capacity to go against a force for a certain amount of distance. And then power is just how quickly can you do it per time. So how much energy or work can you do per second. Okay, the more power you have, the faster you can perform this work. So a powerful thing, if I'm thinking of something to do with that, a powerful thing is say a swimmer. A powerful short distance swimmer is really powerful, but you could have an aerobic swimmer that's slower but can go for a lot longer. So an aerobic swimmer would be able to put in a lot of work and a lot of energy, and would probably outperform in the work and energy area of the quick burst swimmer. This burst swimmer, though, would have more power because they'd be able to go faster distance against that force, or further distance against that force in a shorter amount of time. Okay, so powerful would be the swimmer. All right, so now let's go into the new concept, which is conservation of energy. Has to do with kinetic energy, which we've heard in Science 10 before, and or should have heard, but we're going to be going through it from scratch. And potential energy. So kinetic energy and potential energy. Kinetic energy, what is that? It's just the energy or the work involved in a moving object. Okay, so it's the energy in something that's moving. Okay. You can see that movement is velocity or speed. If that is zero, then your kinetic energy is zero, because 0 times anything is 0. If your mass is 0, your kinetic energy is 0. But nothing really has a mass of 0, so don't have to worry about that. Where did this equation come from? I'm not going to derive it for you, but I'm just going to tell you that it came from the work equation, which is work is force times distance, and kinematics. Okay. It probably came from, I can't quite remember, but probably came from this, v naught t plus half at squared, if we remember that equation. And if you plug that in with the force equation, you would probably be able to get this. Okay, that would be a tough problem to try. Here we go. So now let's just do a couple sample problems, and then we'll get on to potential energy. So kinetic energy, moving things. How much work must be done to accelerate a 110 kilogram motorbike with a 60 kilogram person riding on it from 0 to 80 kilometers per hour. I see kilometers per hour, that's always a problem. We always want meters per second, it's always way better. Works in the equations better. So I'm going to do my conversion. 1 kilometer, to cancel out that kilometer, is 1,000 meters. Now I got to cancel out that hour. 1 hour, I'm going to do a shortcut, is 3,600 seconds. Those cancel, and we're left with meters per second. So if I go 80 times 1,000 divided by 3,600, I get 22.2 repeating meters per second. Okay, so that's the speed that we accelerate to. Okay, so how much work must be done? We know that if the thing is still, it has 0 kinetic energy. So let's just find out what the kinetic energy is at the end, and that'll be how much work we need. Okay, so our EK is half mv squared, which is equal to half the mass, which is them combined, so 170. And then our speed, which we get to 22.2 repeating, squared. We plug that all into our equation, and you should get rounded off 1889. What's the unit? Kinetic energy, or work, is in joules. Okay, and what's joules again? It's a Newton meter. But anyways, you just have to know that it's a joule. So 1889 joules of energy you must put in to get to that speed. Okay, and this is all in effect if there's no air friction or if there's no loss of energy in other means. Okay, so this is the ideal situations. How much work is needed to accelerate a 1 gram bug from rest to 12 meters per second? Okay, so now we're going to look kind of in a smaller dimension than big vehicles. So we know it's EK is half mv squared. So if you notice, it says accelerate, but there's no acceleration in the question. That's a velocity, that's a mass. Okay, so we're okay. We just knowing it's accelerating, but all we need is the final speed. So we know that there's going to be 0 work, and then if it goes, it's going to go half. Our mass is in always should be in kilograms, so 0.01, and then v is meters per second, so we're good there. And then if we plug that in, we get 0.072. What's the unit? It's energy, which is in joules. So 0.072 joules for this bug to get to 12 meters per second speed, which is a lot less than that motorbike. So you can see that mass plays a part. All right, so now we have potential energy, which is energy stored due to position, stress, or electric charge. That's a very simple definition of it. So it's the potential to get moving, essentially. So this is the equation for it. Potential energy is mass times the acceleration of gravity, which is 9.81 mostly, unless you're on the moon, and h, the height, how high you are from the surface of the Earth. Usually you can choose any reference point, but we always go from the surface of the Earth. Okay, so your height from the surface of the Earth, generally. So this is gravitational potential energy. Okay, there's a lot of different types of potential energy, but we're just working with gravity. This equation came from the work equation. Okay, what's the work equation again? Force times distance. Okay, but if you see this, what's force again? Force is a mass times acceleration. So if I change that, it would be mass times acceleration, and then that d is still there. So work is mad. Mass times acceleration times distance. And if you look at this equation, work we know is the same thing as energy. And then we have mass, g is acceleration, and then distance and h, they're just different letters, but they mean the same thing. Okay, so if you see it's really just the work equation. Sample question. What is the mass of a television if it takes 620 joules to lift it 2.5 meters against gravity? Okay, so you can guess we're going to use EP equals mgh. So this time they give you a J. J is joules, so it has to be in for an energy variable, which is not those three, this one. 620. Our mass, we don't know. Gravity is always 9.81 on Earth. And our height from the surface of the Earth is at 2.5. Solve for m. So we got to divide by 9.81 and by that 2.5. We end up getting 25.3. What's the unit? Mass, so it's got to be kilograms. That's how heavy the TV is. So that's really kinetic energy and potential energy on their own. Okay, so now we're going to go into joining them together to find out total energy of a system. Okay, we're really only going to do one sample question here. Law of conservation of energy. We have to go through that. You might have seen it in grade 10. It just means that things don't really lose energy. They just transfer it onto something else, or in the air, or something like that. So it says the total energy of a mechanical system is constant. Energy can be transformed from one form to the other, but the total amount of energy is unchanged. Okay, so that means you can change potential energy to kinetic, and you can change kinetic energy to potential energy. But the total, when you add them up, should be the same in both spots. Okay, and that's what we're going to use for a lot of different questions. And you use it in Physics 12 actually quite a bit to do with orbits as well. So we have Spider-Man, he's on a building. goes down in a spider web kind of like a pendulum. So he has a lot of potential energy. He's not moving, and then he goes down. He's going faster, faster, faster. Down here, he has the least potential energy and the most kinetic energy, and then he'll end up going back up, and that'll transfer his kinetic energy back to potential energy. Okay, conservation of energy says if you don't have any friction, of course, you would go down, you'd go back up to the exact same height, and then you come back, and then you'd reach the same speed down here, and then you'd go back up, 0 speed up here, max potential energy, and then you just keep going back and forth. In real life, they slow down a bit, but that's because it's being transferred through friction or air resistance. All right. So here's the question. Spider-Man shoots a web line 9 meters long. Swings at the end of it like a pendulum. His starting point is 3 meters above the lowest point of his swing. So you have Spider-Man, his rope, he's 3 meters above the lowest spot. So we're going to go, he's going to end up around here. Um, 9 meters long is our pendulum. So how you start these questions is, this is his spot 1, this is his spot 2. Okay, highest amount of potential energy is where he's standing, and then his highest amount of kinetic energy is at the bottom of the swing. So what you write is total. I guess one thing to write is here you see EP plus EK is constant. That's not a very useful equation. What you really use is total energy at spot 1 is equal to the total energy at spot 2. Nothing is lost. And what that translates to is the potential energy at spot 1 plus the kinetic energy at spot 1 is equal to the potential energy at spot 2 plus the kinetic energy at spot 2. Okay, that's the useful equation here. Alright, so total at spot 1 equals the total at spot 2. And then here we can go EP1 plus EK. Oh, not 2. This is total spot 1 still. Potential energy plus kinetic energy is equal to the potential energy at spot 2 plus the kinetic energy at spot 2. Okay? And then now we go through each one individually. Potential energy at spot 1 is just mgh. At height 1, that's why I'm going to put a little 1 there. And then kinetic energy, so he's just standing, he's not actually moving, so this one we can just put a big 0. Potential energy at spot 2, here we're going to assume that it's at 0 height. It might not be at 0 height, but this one's just 3 meters relative to this one. So if it's relative to this one, we can put this one as 0. Potential energy is 0 there. Kinetic energy here will be half mass velocity squared. Okay. So overall our equation now is a lot more simple. mgh1 equals half mv squared. So now when I see this equation, I notice there's an m on both sides, so you can just cross them off. Because if you divide by an m divided by m is just 1. So we end up getting gh1 is half v squared. So masses cancel out. What does that tell us? It tells us that Spider-Man's mass does not matter in this question. That's why it's not even there. Okay? If you first read this question, you'd be like, I need to know the mass. Because both kinetic and potential energy use mass in their equations. But they cancel out, so Spider-Man could be 300 kilograms, 1,500 kilograms, 1 kilogram. It would not matter. You get the same speed no matter what in the ideal world. Okay, so we need to solve for v. So if I multiply by 2 onto the other side, I get v squared is 2gh1. And then we square root. And now we can fill in the variables. V is square root of 2. G is just 9.81. And height at spot 1 is 3 meters. So overall our V is going to be 7.67 meters per second. So that's the answer to this question. It's probably the hardest type question for this section. It's just sometimes you have to go total energy at spot 1 equals total energy at spot 2 is equal to all of this. You zero out some of them and you end up getting your answer. One thing to note, 9 meters we didn't use. So sometimes there's useless information. Usually potential energy and kinetic energy, you just use the vertical height of something. Alright, so that's the end of the lesson. Good luck. The next question, the first practice question, I'm going to give you a hint, and you're going to have to start out with that there. Okay, thanks.